yung nag-cams na tayo. Okay, gets. Then, ngayon, ganun lang uli. May mga papanoodin lang ulit tayong video. And i-discuss ko lang din kung paano ginagawa. Ang gandang expectation natin, wait lang. Open ko lang yung calendar para aware kayo. Medyo nagulo na ang ating sense of time ngayon eh. Papakita ko sa inyo yung calendar ha. Ito yung plan natin. So, tatapos yung ating midterm nitong week ng 9. Pero hindi naman tayo nagklase ng 19-20. October 19 kasi nasa convention ako. October 20, sir, pahinga naman muna. Okay. 26, nag-discuss ako ng midterm sagot. Tapos, anong ginawa pa natin? Yung design project na discussion kung paano gagawin. Then, October 27, naggawa tayo ng CAMS. Nag-discuss pa ng CAMS. So, November 2, hindi din tayo nakapag-klase. Tapos, November 3 ngayon. Ngayon, tutuloy lang natin yung lecture nung sa CAM, kung paano mag-drawing ng CAM using graphical method. Tapos, sa November 9 is paano mag-drawing ng CAM using analytical method. So, mas mahirap itong 9, pero kaya na yun. Then sa 10 is design plate number 3 na tayo. So November 10. Yan. Design plate number 3. Then 16 saka 17 is discussion naman tayo ng gears. Tapos 23 gears pa din. Then 24 is design plate number 4 naman. Kung magdodrawing naman tayo ng gears. So, meron na tayong schedule. November 10, 24. Then, ito ngayon ang hindi ko pa alam. Itong December 7 and 8. Kasi nangyari dito sa atin sa midterm, napaga eh. Naging October 12, 13 yung midterm. Eh, supposedly week 9 yun, which is 1920. So, ngayon, i-mindset nyo na ang December 1 is design project presentation. So, anong nangyayari dyan? Ulitin ko. So, November 10 is design plate number 1. Ay, 3 pala. Okay. Design plate number 3. Ito naman design plate number 4. Tapos December 1 is design project presentation. Tapos 7, 8. Supposedly, lagi namang dapat finals is 14, 15. So, nangyayari lang, dito kasi sa ME. So, since ang dami kasi natin, nagiging more than 1 week yung exam. So, baka maging finals to. So, mangyayari dyan, pag nag-design plate number 4 tayo sa November 24, ang November 30 ay hindi ko sure kung may pasok. Kasi supposedly is Andres Bonifacio Day, which is a holiday. And parang hapon, which is a holiday. And malamang walang pasok. Nangyari lang kasi dati na ang ginawa ni Marcos, ni President Marcos, minumove niya yung holiday ng Friday. So kung magkakaroon ng announcement na mamumove yung holiday ng November 29, is may pasok tayong 30. So kung hindi siya i-move, wala tayong pasok. So, ganun na yung gagawin nating mindset. Tapos, December 1, dapat gawa na yung, bago mag-December 1, dapat gawa na yung chapter 1 to 5 nyo. Dapat meron na kayong slideshow, presentation. Then, i-send nyo na sa akin as advance copy. Para during presentation is may susundan ako. Ngayon, December 1 is odd week, which is week 15. Ngayon, kung matutuloy yung presentation, edi online tayo. Ngayon, kung ang finals natin hindi pa naman gaganapin ng December 7, 8, ay sa December 8 tayo magpa-present, which is face-to-face. Okay? So, ulitin ko ang schedule natin ha. So, ngayon is November 3. Then, ang gagawin natin ngayon is discussion pa din ng paano mag-design ng cam using graphical method. Then, November 9 is design ng cam using analytical method. Then, November 10 is design plate number 3. So, face-to-face tayo na. Then, 16 is discussion ng gears. 17, discussion ng gears. I think sa 16, 17, matatapos na natin yung discussion ng gears sa dalawang session. And sa 23 is yung last topic, which is the belts, pulleys, chains, which is kaya naman ng isang session lang. Puro identification naman yan. Puro terms. Then 24 is design plate number 4. Then November 30 is possible holiday. Meaning, December 1 is design project presentation. And sa atin is December 7 and 8. Ito yung hindi ko pa sure eh. Ulitin ko, kung hindi pa to finals, sa December 8 tayo magpe-present. Pero kung finals na ito, December 1 tayo magpe-present. So, paano natin malalaman? Malalaman natin before November 30. So, before November 30, alam na natin yan kung finals ba tong 7 and 8. And, yan. Then, supposedly, wala na tayong pasok niyan. So, any questions sa schedule natin? Clarifications? Kung December 8 tayo makakapag-presentation, kung hindi pa finals to, face-to-face tayo. Kaya anong dapat suot? Casual lang, org shirt, or basta yung makakapasok kayo dito sa school. Tapos, ano pa? Yan lang. So, any question regarding our schedule? Okay. So, mag-start na tayo ng klase. Wait lang. Check ko lang ito. Kung mang-aakit ka na naman. Ay, gumana. Wait lang ha. Ay, gumana na itong something ko. Mamaya na lang. Okay. I think nakadalawa tayong video last time. So, meron pa akong iba pa dito. Ito naman sa video na to is ang follower is knife edge type. Warning ulit dun sa mga naka-earphones. Medyo malakas yung sound. Kaya pakihina na lang para di kayo magulat. Tapos dito sa video na to ay tingnan natin kung anong
Video
pinagkaiba niya.
will try to understand how to draw cam profile. Now in this case, we have to draw a cam profile to operate a knife edge follower using the following data. The outstroke of the follower is 120 degree with simple harmonic.
Outstroke, again, pag sinabi nating outstroke, ito yung part ng movement ng cam tsaka follower from the starting position hanggang dun sa highest point niya. So, di ba pag follower, it's either reciprocating up and down or oscillating up and down pa rin siya pero naka-arc. Pag outstroke, from the starting position hanggang dun sa pinakamataas niyang position. So, it would take 120 it would take 120 degrees of cam rotation. Ibig sabihin, kung imagine nyo yung cam, nag-rotate siya ng 120 degrees, then, ang motion niya is simple harmonic motion. So based on the lecture natin, we have 4 different types of motion kapag graphical method, which is the parabolic, constant acceleration, deceleration, the parabolic, constant velocity, then this simple harmonic motion, at saka yung cycloidal motion. So dito sa outstroke, 120 degrees, simple harmonic motion. Then pag sinabi nating dwell, kasi nga ang outstroke is from the original position hanggang doon sa highest position niya. When you say dwell, this is the time or the rotation that it will stay in place. So for the 60 degrees cam rotation following the 120 degrees, it will stay on the top position or it will stay on the highest position for 60 degrees rotation.
Then outstroke dwell is 60 degree.
Then when we say return stroke, this is the cam rotation from the highest point going back to its original position. So if again, to review, for the outstroke, this is the cam rotation from the original position going to the highest position. Then the dwell is how much the cam will stay in place or the follower will stay in place. Then return stroke is from the highest position going back to the original position. For simple harmonic motion, SHM, the method on drawing the curve is we will draw a semicircle or a half circle. Then we will divide it into parts. Then we will make a cam displacement curve and we will also divide it into parts. So, and how many we divide the semicircle, that's how many we will divide the cam displacement curve. Then, we will just trace the lines. You will see later on this video. And for the uniform velocity, this is the same as parabolic constant velocity. We will simply just draw a diagonal from one end to another. Since this is the return stroke, we will just make a diagonal from the highest point going to the lowest point.
Return stroke is 120 degree with uniform velocity and dwell for the remaining period of cam rotation. Lift of the follower or stroke of the follower is 30 mm and least or minimum radius of the cam is 5 cm. And we are assuming that the cam rotates.
Now, this second item, and this fourth item, which is dwell for the remaining period of cam rotation. So, what is the remaining period? We have the outstroke, which is 120 degrees. Then the outstroke dwell is 60. So if you add it, you have 180, meaning we already have 180 degrees of cam rotation. Then if we add the return stroke, which is 120 also, we will have 300 degrees. So the remaining cam rotation is 60 degrees, meaning the remaining 60 degrees is how long it will dwell before it starts with the outstroke again. So you will see again in the video later. When we say lift of the follower is 30 mm. So this is the height on which the follower displaces. So this is the highest point that it will reach. Meaning, it would take 120 degrees of rotation for outstroke to reach the lift of 30 mm. Then it will take 120 degrees of return stroke to return the 30 mm going back to zero. Then list or minimum radius of the cam. This is the base circle. So if the base circle is given, which is 5 centimeter, this is radius. We can draw the circle once we have the radius. Then cam rotates in clockwise direction.
in
Okay.
clockwise direction. So for this specification, we have to draw the cam profile. Now, first we'll see how to draw the displacement diagram in this particular case. Then we'll actually construct it, and then we'll see the with the help of animation how to actually construct it so that you can easily understand the given procedure.
He is calling the graph the displacement diagram, but it's the same thing as the cam displacement curve. So they're the same. It's just a different name. So again, how did we come up with this cam displacement curve or displacement diagram? This first part, the curve on the left side, is based on the given, which is 120 degrees of outstroke. So they say it's for us to draw the 120 degrees, we have to make a scale. So the scale he made here is 1 centimeter is to 20 degrees. So that's why he has 6 centimeters in the outstroke. Then he placed a semicircle on the left side and divided it into 6 parts. So the displacement diagram is also divided into 6 parts. Then he'll make a line from the division of the semicircle going to the displacement diagram, and it will intersect at these lines, and we will just trace the intersections. So this is simple harmonic motion. Then on the center side, this is the dwell. So again, if dwell, it means it stays in place, meaning there should be no curve in the dwell because it stays in place. Then for the return stroke, it is mentioned that it is on constant velocity. Again, for constant velocity, we will just have to draw a straight line, just like this. So there is no curve. Then, uh, since the given is 120 degrees of return stroke, so we will have to draw the 120 degrees again. So for this, he used 6 centimeters also. So that's why this is the breakdown of the curve. Again, this is the scale that he used. For the x-axis, he represented the 120 degrees with centimeters or linear distance. So he used, for every 1 centimeter, there is 20 degrees. So that's why there are 6 centimeters on the outstroke. Then for the dwell, we have 60 degrees. So we have 3 centimeters. Then for the return stroke, since it is also 120 degrees, we have the 6 centimeters also. Then for the y-axis, the given lift is 30 mm. So meaning, we have to draw 30 mm from 0 going up. So that is 30 mm.
Now here we have taken the space diagram scale. So on x-axis 1 centimeter is 20 degree of the cam rotation. So you can see over here the outstroke, as we have seen, it is 120. So 120 divided by this 20, so it is 6 centimeter. So this particular length will be of 6 centimeter, and we have divided that into, suppose say, 6 equal part. Then the next is outstroke dwell, that is 60 degrees. So 60 again divided by this 20, that is the 3 centimeter. So this length will be for 3 centimeter, as you can see over here. Similarly, this return stroke is of 120 degree. So it is 120 divided by this 20, that is 6 centimeter. Then as this outstroke is with simple harmonic motion, we have constructed this semicircle over here, and we have divided it into 6 equal part. Now from point 1, draw the
Okay. For this step, once we have divided the semicircle into parts, we'll just make a straight line parallel to the x-axis, and the starting point is this, the numbers 1, 2, 3, 4, 5, 6.
horizontal line. From point 2 also draw the horizontal line, so that it will intersect this second line over here. From point 3 draw the horizontal line, so that it can intersect over here at this particular point, and name those particular parts. So as you can see over here, the horizontal line which we have drawn from 1 will intersect this our line from the first point at point A. Similarly, this horizontal line will intersect this particular vertical line at point B, and so on. And then draw a smooth curve that is passing through these particular points. Then there is a dwell period, so it will remain at this particular position for 60 degree of rotation. Then the return stroke is of uniform velocity, so join this diagonal like this.
Okay. Since again, this is a constant velocity, but he uses the term uniform velocity. It's the same thing. We'll just make a diagonal.
And these are the points, that is F, G, H, I, J, K. These are the distances which are important for us. So all these distances, that is 1A, 2B, then this 3C, 4D.
Then we will measure the distance from the x-axis going to these letters A, B, C, D, E, F, F, G, H, A, I, K, L, M. Then once we measure these distances, we will transfer it to the base circle.
All these distances are important for us, not only for this outstroke but also for the return stroke. Now we'll see this particular construction with the help of animation. One more thing, that on y-axis we are having the scale as 1 centimeter is equal to 1 centimeter of the lift of the follower. Our lift of the follower is 30 mm, that is 3 centimeter. So this vertical distance will be of 3 centimeter. Now let us see how to construct this particular displacement diagram. We'll see the entire construction also afterwards in full animation form. So as explained earlier, we are drawing this displacement diagram.
This is the animation part on how it arrived, how the displacement or the cam displacement curve was made.
Dividing the semicircle, then drawing the vertical lines, then horizontal lines from the given particular part, and then a smooth curve passing through those intersection points of A, B, C, etc. Similarly, in case of the return stroke also, we'll get this type of the construction. This we have already seen. Now let us see how to draw
Then once we have drawn the cam displacement curve, we will now draw the base circle.
actually this particular cam profile. Now we know that the least radius of the cam is 5 centimeter. So we have drawn this circle of 5 centimeter. Then outstroke is 120 degree. Divide this circle into 6 equal part as shown over here.
Then, since it is given that The outstroke is 120 degrees. The starting point of the cam is the top part. Then, since it is given that the outstroke is 120 degrees, starting from the starting point of the cam, we will measure 120 degrees. So this is the 120 degrees, the given drawing here. Then since we have divided the outstroke into six parts, we will also divide this 120 degree into six parts.
during the outstroke. Then there is a dwell period. Then again divide the return stroke into 6 equal parts and draw these lines passing through this. Now, as you can see over here, these are the distances which we have measured, correct? 0.75, 1.5, 0.25. Those we are transferring over here on these lines. And then we are drawing a smooth curve passing through these particular points. So this is for the outstroke. Then there is a dwell period.
Okay, so this red line here is brought about by measuring the distances here at the displacement curve, then transferring it to the base circle. So this point 2, point 75, 1.5, 2.25, 2.8, and 3. These measurements is transferred to the our base circle. Then for the next part, we have the dwell. So we'll just have to draw 60 degrees. So this space here on the lower left part is 60 degrees. Then we'll make another 3 mm, 30 mm to make the dwell.
From this to this, there is a dwell period. Similar to this 3 centimeter, 2.5 centimeter, 2 and 1.5, those points they are also plotted over here, and we have drawn a smooth curve, that is this particular green curve passing through that those particular points. So this blue line represents the what we can say outstroke. Then there is a outstroke dwell.
So this blue line, this is the dwell. So then for the green line, this is the return stroke. So if you will see, this is not a mirror image of the outstroke because they use different curves. But it looks the same. It looks similar.
And then there is a return stroke. So all these distances, that is 3 centimeter, 2.5 centimeter, 2, 1.5, 1.5, these are all transferred over here. So this is 3, 2.5, then 2, 1.5, 1.5, etc. for this return stroke. Similarly, for this outstroke also, we have transferred all these distances over here. Now, we'll see how actually we'll draw this particular diagram. So let us start with our actual drawing of the cam profile.
So again, this is another. This is just another animation on how to draw.
So as the outstroke is of 120 degree, divide it into 6 equal parts. So we are dividing this outstroke of 120 into 6 equal parts. Then there is a dwell for 60 degree. Again, divide the return stroke into 6 equal parts. Now we'll draw the displacement diagram also simultaneously over here, which we have already seen how to draw it and how to measure the distances, and those distances will transfer on these particular lines. First, we'll start with the outstroke, as you can see over here. So as the outstroke is with simple harmonic motion, we'll draw the semicircle, then divide that particular semicircle into 6 equal part. 180 divided by 6, so 30-degree angle we have taken, so that we can divide that circle into 6 equal parts. Then locate these particular points on our semicircle. join this with the center. Now transfer these points on the corresponding lines, vertical lines which we have drawn, and draw a smooth curve, that is a simple harmonic motion. Now the points which we have marked on our circle, transfer the given particular distances, as you can see over here on those lines, and then draw a smooth curve passing through this particular point. So we are drawing these points of intersection with the line of this arc. So this is our cam profile during the outstroke. There is a dwell for the remaining degree. So we have just drawn a curve over here. Then the return stroke is with uniform velocity. Again, divide that particular return stroke of 120 divided by 20, that is 6 centimeter, into 6 equal part, and join this diagonal. And these distances, they are important for us, so we are marking this point so that we can transfer these distances as we have seen earlier on our this particular blue lines. So we are just marking the points on our circle. Now transfer these distances. Mark this point of intersection of this arc with these blue lines, and then draw the curve. So this is our complete cam profile. Thank you very much for watching.
Okay, so that's how we draw the cam profile using graphical method. So I have another video here, so let's watch again.
To draw cam profile. Now we have to draw a cam profile in case of a knife edge follower using the following data. Minimum radius of the cam is 5 centimeter. Then outstroke is 120 degree with simple harmonic motion. Outward dwell is 60 degree. Return stroke is 120 degree with simple harmonic motion, and dwell for the remaining period of cam rotation. Stroke or lift of the follower is given as 6 centimeter. So the data is written over here. So outstroke is 120, outstroke dwell is 60 degree, return stroke is 120 degree, and remaining angle will be return dwell, that is 360.
Wait. So here, the given is changed a bit. So for this one, we have the outstroke still 120 with simple harmonic motion, but the return stroke is also simple harmonic motion. So this is a similar case with the other one. It's just the outstroke is different.
Harmonic motion, and dwell for the remaining period of cam rotation. Stroke or lift of the follower is given as 6 centimeter. So the data is written over here. So outstroke is 120, outstroke dwell is 60 degree, return stroke is 120 degree, and remaining angle will be return dwell, that is 360 minus the summation of all these three particular angles. So it is 360 minus 120 plus 60 plus 120. So that will be nothing but 60 degree.
This SRH is the lift. It's just a different name again. We can use S as a replacement for displacement or H as the height of displacement.
Lift or stroke of the follower is given as 6 centimeter, and minimum radius of the cam is given as 5 centimeter. Now the important part is to select the scale over here. So scale that we have.
Again, for the scale, to represent the 120 degrees of outstroke, to represent the outstroke dwell, to represent the return stroke, here's for every 20 degrees, there is 1 centimeter. So this is not a rule, so we can change what scale we want, but it is easier to use this scale.
we have chosen is 1 centimeter is equal to 20 degree on x-axis of cam rotation. Then 1 centimeter is equal to 1 centimeter on y-axis of lift or stroke of the follower. So outstroke is equal to 120 degree. So 120 divided by scale that we have chosen is 20 degree. So this 120 divided by 20, that is 6 centimeter. Similarly, theta OD is equal to 60. So 60 divided by the scale, that is 20 degree. So it is 3 centimeter. And theta R, return stroke angle, is 120 divided by 20, that is 6 centimeter. So on our displacement diagram, we are going to represent these three particular angles which are required for the displacement diagram as 6 centimeter, 3 centimeter, and 6 centimeter. Similarly, on y-axis, 1 centimeter is equal to 1 centimeter. So on y-axis, 6 centimeter stroke will be representing by the original length of 6 centimeter. So let us first draw the diagram for this displacement diagram for this.
Again, using the scale, we can draw the displacement diagram or the cam displacement curve. So for every 1 centimeter, we have 20 degrees rotation. The different case here is he also included the drawing for the return stroke. So it is not required, but he just wanted to include it. So the last space here
So
on
we
the
have
right side,
considered the 6
this
centimeter
is
length
the
of the
return
outstroke,
stroke
then
dwell.
3 centimeter length for the outstroke dwell, and then the 6 centimeter length for the return stroke. So outstroke is 120 and by scale it is 6 centimeter on our displacement diagram. Outstroke dwell is 60 degree. It is by 3 centimeter on our displacement diagram. And return stroke is 120. So it is 120 divided by 60, that is 6 centimeter on our displacement diagram. Then we are not considering this particular theta return dwell part over here. So we are concentrating only on these three particular angles for drawing the displacement diagram. Now we'll draw the center line. Now, as it is a simple harmonic motion, we'll divide this particular semicircle into six equal parts. So it is 180 divided by 6, that is 30 degrees. So we
So
have
again,
marked the angles.
for simple harmonic motion, we will have to divide the semicircle into parts. So if we divide it into 6 parts, so the displacement diagram should also be divided into 6 parts. Now, since the return stroke is also simple harmonic motion, we can just extend the lines here. We don't need to draw a semicircle on the right side.
Of 30 degree over here. Now draw the lines passing through this. Then mark this 1, 2, 3, 4, 5, and 6. Draw the horizontal line from this one till it intersect this vertical line from 1 at this particular point. Similarly, draw a horizontal line from 2 till it intersects this vertical line from 2 at this particular point. Same procedure we have to draw for line from 3 till it intersects this vertical line from 3 and so on. Now we have to join these particular points by a smooth curve. So this is the simple harmonic motion curve that we have obtained for theta O is equal to 120 degree. Now, as both, that is the outstroke and return stroke, they are of the simple harmonic motion, we can transform these particular points or we can translate these particular points on the return side also. So as you can see over here, the similar points.
Okay. So again, since the return stroke is also simple harmonic motion, he is just copying the points to the return stroke coming from the outstroke.
Same points will be there for the return stroke also. And then join a smooth curve from this particular point. So this is the curve for return stroke. And then this is the dwell. So we have completed this over the displacement diagram in case of this particular problem. Now we draw the cam of 5 base circle of 5 centimeter radius, and then we'll divide, taking this particular vertical line as the reference. We'll divide the given particular base circle in 6 equal parts of 20 degree for our outstroke, because our outstroke is of 120 degree. So 120 divided by 6, that is 20 degree. So these are the lines which we have drawn of 20 degree from the center of this particular circle.
Okay,
Then
again, since the given is 120 degrees for outstroke, we have to mark the line of the 120 degrees, then divided into parts on how many parts we have divided the displacement diagram.
remaining 60 degree is for dwell. So from 120 to 180, correct? Or this is the 60-degree angle which we have drawn over here. Then we'll draw the lines for the return stroke, which is also of 120 degree. So these are the lines which we have drawn for return stroke. So it is from this 0 to 6, these are the parts for our outstroke. Then this is the 12, and this is our 6 to 12, these are the return stroke part. So as we know that this particular is theta O, then 12, and then there is a return stroke. Now we'll transfer this 1A distance over here on this 1A. Then this 2B distance from 2 to B over here on this line. Then from 3 to C, it will be on this particular line, and so on. So first we'll measure this particular distance. So as you can see, we have measured this distance. So we have drawn this line over here. So this particular distance we have to mark over here. So we'll be marking that particular point. So it is 1A distance is marked over here. 1A distance is marked. Similarly, we'll now
Again, as same with the other method, we just copy the distances made in this curve to the base circle for us to draw the cam profile.
draw, or we'll mark this distance to be over here. So this is 2B distance as indicated by this dark line and this 0. So that we are marking over here. So this is 2B distance. This 2B distance is marked over here. Similarly, this 3 and C distance, that is 3 centimeter, that we are marking over here. That is 3C distance. Similarly, for 4D, then for 5D, and then for this particular 6F. Similarly, this 6F will be drawn on the return stroke lines also. So all these particular points are drawn. So it is 6F, then 7G, 8H. So all these lines 6F, 7G, 8H, these distances they are transferred over here on the corresponding lines. Now we have to draw a smooth curve passing through these particular points, and that will be our cam profile.
Yung pagka-drawing ng curve dito, we'll just use a French curve lang.
So as you can see over here, this is the curve cam profile that we have drawn. This is the dwell period, and so this from 0 to 6, it is the outstroke. Then there is a dwell from F to F, and then from F to this particular L part, correct? It is nothing but what? The dwell, and then it is nothing but the return stroke, and then there will be a dwell period of 60 degree. So that will complete our complete cam profile. So in this way, we can draw a cam profile in case of this particular knife edge follower having simple harmonic motion during outstroke as well as during the return stroke. Thank you very much for watching.
Okay. Again, so that's the design of, wait, cam profile using simple harmonic motion. So that's the easy part. Drawing the cam profile when the follower is reciprocating. So if the follower is oscillating, it is much challenging. This is it is more challenging to do than the reciprocating. So for the oscillating part, we have to consider the length of the arm. We have to consider the distance of the pivot of the oscillating arm. So I'll just give you a overview how to design this, but this is a hard one compared with the others.
In this video, we'll see how to draw cam profile in case of oscillating roller follower. So let us start with the problem statement. So we have to draw a cam profile to drive an oscillating roller follower with the following specifications. Follower to move outward through an angular displacement of 20 degree during the first 120 degree of cam rotation. Follower to return to its initial position during next 120 degree of cam rotation. Follower to dwell for the rest of 120 degree of cam rotation. The distance between the pivot center and roller center is 120 mm. Then distance between pivot center and cam axis is 130 mm. Minimum radius of the cam is 40 mm. Then roller radius is 10 mm. Outstroke and instroke, both stroke takes place with simple harmonic motion.
Okay, let's analyze the given first. The follower to move outwards through an angular displacement of 20 degrees during the first 120 degrees of cam rotation. So since it is given that the follower is oscillating, the given displacement is 20 degrees. Meaning, again, if we have an oscillating motion, it is a back and forth motion on an angle. So the angle that it makes is 20 degrees. And it can make 20 degrees of travel during the 120-degree cam rotation of the cam. Then the follower will return to its position during the next 120 degrees. So meaning there is no outstroke dwell. Once it had reached the 120 degrees, it will now return to its original position for the succeeding 120 degrees. Then once it has returned to its original position, it will dwell on the 120 degrees of rotation. Then another given here is the distance between the pivot center and the roller center. So the roller center, the following given is a roller follower, meaning that we will have a prime circle. Then the pivot center is, this is the joint that is connected to the ground. And this 120 mm is the distance of the joint going to the center of the roller. Then the distance between the pivot center and the cam axis, when we say cam axis, it is the center of the base circle. So the given, there is a distance of the pivot of the follower going to the center of the cam. We have 130 mm. Then, minimum radius of cam, we have 40 mm. So meaning the base circle is 40 mm for the radius. And the roller radius is 10 mm. Again, if we have a roller, we will make a prime circle. First, let's draw the base circle, then another circle outside it. We will call it the prime circle. This is for the consideration of the roller radius. Then, given the motions of the outstroke and the instroke are both simple harmonic motion. So the instroke is another name for the return stroke. So if the outstroke, the opposite of out is in, so that's why outstroke, instroke. Again, if we have simple harmonic motion, we will draw a semicircle on the side to draw the curve. And the first thing we will do here is draw to determine the linear displacement. So if you will notice here, there is no given height or the displacement of the follower. On the past examples, we have given, for example, 30 mm displacement or 60 mm displacement. The y-axis is given. But here, the given displacement is 20 degrees. So how can we draw 20 degrees into the y-axis? So if the cam rotation on the x-axis, we will just use the scales. But for the y-axis, it is different.
So using this
So what
data,
we will do
we have to
is
draw the cam
compute
profile.
for the length of the arc. Again, the given angle is 20 degrees. This 20 degrees is, uh, wait. This 20 degrees is the travel of the follower. So this arc can be computed using radius times the angle in radians. So 20 degrees in radians times the radius, which is given is 120 mm, we will have
So
now the displacement.
as you can see over here, the oscillation
So let's convert 20 degrees into radians. By converting it, we'll just multiply it by pi over 180. Then multiply it with the radius, we will have now the displacement. Then the displacement here will be rounded off to the whole number, and we will use this as the y-axis.
is given as 20 degree. Oscillation of the follower is given as 20 degree. So convert that value into radian. So we have multiplied it by, so 20 into pi by 180, that is pi by 9 radian. Now A1A is the distance between the pivot center and roller center. So this is the A2 is the roller center and A1 is the pivot center, and that value, that distance is given as 120 mm. So this is our radius. Then arc AA2. Now we know that arc S is equal to r theta. So radius is 120 and theta is pi.
Okay, after multiplying the radius with the angle in radians, we will have 42 mm. So we will use 42 mm on the cam displacement curve on the y-axis. Again, I'll just repeat this procedure. For oscillating follower, it is a back and forth motion on an angle, and the given angle is 20 degrees. It is given that the distance between the pivot and the roller center is 120 mm. So we can use this as a radius. So to compute for the linear displacement, this S, we will just have to multiply the radius or the distance between the pivot and the roller center multiplied by the angle in radians. So that's why this 20 degrees is first converted into radian form by multiplying it to pi over 180. Then, we will multiply this pi over 9 into 120. Then the answer is, in there is a decimal, so we will have to round it into whole numbers. Then the answer, 42 mm, this is now what we will use on the y-axis for the cam displacement curve.
Pi by 9. So this value comes out to be 41.887 or nearly 42 mm. Now this arc distance will approximately will be equal to this vertical distance. So we can say that the lift of the follower is 42 mm in case of drawing the displacement diagram. Now theta outstroke is given as 120 degree with simple harmonic motion. Return stroke is also 120 degree with simple harmonic motion. Then return dwell is also 120 degree. Minimum radius of the cam is 40 mm. Then radius of the roller is 10 mm. Therefore prime circle radius will be equal to 40 plus 10, that is 50 mm. Convert these values into in centimeters, so it is 5 centimeter. Now we'll take into consideration the scale, which is very, very important. So on x-axis, we are having a scale of 1 centimeter is equal to 20 degree of cam rotation, and on
Okay, for this one, again, he used 1 centimeter is to 20 degrees for cam rotation. Again, this is not a rule. It is just convenient to use this. So we can use this also. Then minimum radius of cam is 4 centimeters. We can use this as a base circle. And since we have a roller radius, we will have a prime circle.
y-axis, we will take 1 centimeter is equal to 10 of stroke or lift of the follower. So you can see 120 divided by 20, that is 6 centimeter. So theta outstroke will be 6 centimeter. Similarly, theta return stroke is also 120 divided by 20, that is 6 centimeter, and theta return dwell is also 120 divided by 20, that is 6 centimeter. So total will be 18 centimeter, out of which the outstroke and return stroke, they are important for us while drawing the displacement diagram. So first we'll mark the length of 18 centimeter, then divide the outstroke and return stroke in 6 equal parts as shown over here. So
Okay, so for the cam displacement curve part, since the given is 120 degrees on the outstroke, so the representation of that will be 6 centimeters.
as you can see, the lift of the follower is 42
The earlier computed 42 mm will be placed on the y-axis. Then for the
mm.
x-axis,
So the arc distance which we have approximately converted into the vertical
using
displacement.
the scale
Then outstroke
of 120 degrees is to of 20 degrees is to 1 centimeter,
is
we
120
will
degree,
have 6
return stroke is
centimeters
120
for
degree, and
outstroke
return dwell is also
and 6 centimeters for return stroke.
120 degree, and all of them are 6 centimeter by scale, and we have divided that particular 6 centimeter into 6 equal part. Now as it is, the motion is a simple harmonic motion, we'll draw a semicircle.
Okay, again, for simple harmonic motion, we will draw the semicircle first, then divide it into parts. Since we have divided the outstroke into 6 parts, we will also divide the semicircle into 6 parts. For this cam displacement curve, it is not required to draw the return dwell. But for clarity, they have drawn the return dwell here. But technically, we cannot we can choose not to draw the return dwell.
Of radius 42 divided by 2, that is 2.1. 42 divided by 2, that is 21, that is 2.1 centimeter. 21 that is 2.1 centimeter. Now we have to divide this semicircle into 6 equal parts. So 180 divided by 6, that is 30 degree. So we'll draw lines of 30 degree, as you can see, and then we'll mark these points. So you can see this is 0, 1, 2, 3, 4, 5 and 6. So we have divided this semicircle into 6 equal parts. Now we have to draw projection from point 1, 2, then 3, 4, 5, like that. So the projection drawn from 1 will intersect this one over here at this point. Similarly, it will intersect this 11th vertical line at this point. From 2, it will intersect over here at this point. Similarly, it will intersect the 10th point over here. Now as the motion is simple harmonic motion for both outstroke as well as return stroke, we have extended this point over here on the return side also. This third line, the third projection will intersect this vertical line at point 3, as well as it will also intersect this ninth vertical line from 9 at this particular point, and so on. So look at these points and draw a smooth curve passing through these particular points like this. So this is the rise and this is the return stroke. This is the outstroke motion with simple harmonic motion, then return motion during the return motion using the simple harmonic motion.
Okay, again, since there is no given outstroke dwell, so after the outstroke, it will proceed directly into the return stroke.
Now for us, these points A, B, C, D, E, F, G, H, I, J, K, these points, they are important. So first we'll measure distance 1A, 2B, 3C, 4D, 5E, 6F, then 7G, 8H, 9I, 10J and 11K distances. Now as you can see, 1A distance will be same as 11K, then 2B distance will be same as 10J, 3C will be same as 9I and so on. So let us measure those distances first. So 1A distance comes out to be approximately 0.3 centimeter, then 2B distance is 1 centimeter, 3C distance is 2.1 centimeter, then 4D 3.1 centimeter, 5E 3.8 and 6F 4.2 centimeter.
These measurements will be transferred into the prime circle. So not the base circle because we have roller radius.
So using these distances, now we have to draw the cam profile over here. So first we'll draw the base circle, which is of 4 centimeter. So minimum radius of the cam is given as 4 centimeter. So we have taken a radius of 4 centimeter and then
So this is the hard part again. So for this one, we have to first draw the base circle. So the base circle is this big circle here in the middle. Then we have to draw the prime circle. So the prime circle is the outer circle here. Then we have to draw the distance of the pivot going into the roller, which again is 120 mm. So 120 mm is the straight line horizontal here on the upper side. Then it is also given that of uh, the distance of the pivot with the cam axis, which is the cam center, is 130 mm. So this diagonal here is 130 mm. Okay? So again, first, let's draw the base circle, which is given as 4 centimeters. Then, we have to draw the prime circle, given that the roller radius is 10 mm. So we can draw the outer circle or the prime circle. Then let's draw the location of the pivot, which is given is 120 mm distance from the roller going to the pivot, which is also 130 mm distance from the pivot going to the cam axis or the center. So this diagonal is 130 mm. This straight line is 120 mm. This big circle, this outer circle, is brought about by the 130 mm distance of the pivot with the axis, with the cam axis. So since we have divided the outstroke into 6 parts, then we have divided the return stroke into 6 parts also. We will also divide this big circle into 6 parts outstroke and 6 parts return stroke. Okay? First, we'll have, since it is given that for every part we have 20 degrees, so let's just draw 20 degrees here. So you will see that's here on the big circle, on the outmost circle. So this is divided into 20 degrees for outstroke and return stroke. Then, for this part, we will need a compass. What we will do is make the compass center on this the pointed part of the compass going on the outer circle, this big circle. Then we will have to make a 120 mm distance, and we will have to make a line that will pass through the prime circle. This is what we're doing is we are projecting the rocker arm or the oscillating arm to the cam by rotating it into the cam. So again, the outer circle, this big circle, is divided into 6 parts outstroke and 6 parts return stroke. Then these points will now be the center or the pointed end of the compass. Then we will make 120 mm distances going to the prime circle. Then the distances we have measured on the cam displacement curve, we will project into this prime circle.
We have drawn the base
Again,
circle
this
or
is very
roller
hard
radius circle of the
compared
cam.
with the
Then
others.
prime circle, add the roller radius 4 centimeter plus 1 centimeter. 1 centimeter is the roller radius, so 5 centimeter. This is the another circle, which is the prime circle, as we have already seen. Then the pivot circle, which is of 13 centimeter. So the distance between the cam axis and pivot center is 13 centimeter. So draw another circle which is of 13 centimeter radius as indicated in the diagram. Now we'll take this point as a center and we'll draw a roller of a radius of 1 centimeter. So we have drawn this roller which is of 1 centimeter length. Now we know that the distance between the pivot center and the roller center is 12 centimeter. So we have to choose the arc of 12 centimeter. We have to choose the radius of 12 centimeter and then we have to draw an arc. So let us do that particular thing over here. So we'll take a radius of 12 centimeter and then we'll draw an arc so that that particular arc will intersect this circle pivot 13 centimeter radius circle, correct, at certain point over here. So that is also shown in the procedure. So you can see this is the point. So this is the pivot center. So pivot center is joined over here with the roller center and pivot center is now joined over here with the cam axis center or cam center. So this will complete our first part. Now we have to divide this particular circle, that is the pivot circle, into 6 equal parts. So 120 divided by 6, that is 20 degree. So these are all 20-degree angles, correct. So outstroke is also divided into 6 equal parts and return stroke is also divided into 6 equal parts of 20 degree, because outstroke is 120 and return stroke is also 120. So 120 divided by 6, that is 20. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 parts, inclusive of outstroke and return stroke. Now from this point 1, we have to draw arc of 12 centimeter on this prime circle. So that procedure will be shown over here. So as you can see, taking this as a center and radius is equal to 12 centimeter, we have to draw an arc of 12 centimeter on the prime circle. So this is the 12 centimeter radius point and draw the arc as shown in the animation. So this is our first arc. Then taking point 2, draw another arc of the same centimeter, that is 12 centimeter. So that also we have shown over here. Then put this over here at the third part and then draw the arc and so on. So we have to go on marking this particular arcs from the respective points. So now it is the fourth point and again draw the arc over here like this and so on. So you can easily understand this particular procedure, so that we are drawing the arc continuously from the respective points. Now on this particular arcs, we have to mark the distances which we have noted down, that is the distances of 1A, 2B, 3C, 4D, 5E, 6F and so on. So all these distances we have to put on this particular arc. For example, 1A distance is 0.3 centimeter, correct, and another distance was 0.8 and so on. So all these distances will put over here. So after completing this, first we'll mark the distance of 0.3 over here on the first line. So as you can see, we have marked 1a over here. Then the distance of 0.8 on the another line. So that also we have marked over here. Then of nearly 1 centimeter, 1.1 centimeter. That distance also then of 2.1 centimeter. So all these distances are marked on this. Now using those points, that is 1a, 2b, with a as a center and taking roller radius, we have to draw the roller.
Okay, so once we have transferred the distances into this arc, the endpoints will we will now draw the rollers. So once we have drawn the rollers, like this one, we will now trace the cam profile.
Rollers over here like this. Then taking this B as a center, we have to draw circle like this. Then taking this C as a center, we have to draw the roller radius and so on. So we can go on drawing this radius. So this is, so once again this is 1A, 2B, 3C, 4D and the other distances. So we have marked all this, we have drawn this roller from the respective points till the end. So let us now repeat this procedure in our next animation. So as we have discussed earlier, we have drawn the given particular.
Okay, once we have drawn the rollers on the centers here, we will now trace the cam profile.
Rollers. So this is O, A1, A, correct? O is the cam center. This is the roller center. A1 is the pivot center. Then these are the 12 parts which we have made of 20 degree each for outstroke as well as for the return stroke. Then with 1 as center and arc distance is equal to A1, that is 12 centimeter. We have drawn the arcs over here. And then on this, we have transferred the distances 1A, 2B, 3C, 4D, 5E, 6F, 7G, 8H, 9I, 10J, 11K and so on. With A as a center, we have drawn these rollers. With B as a center, we have drawn the roller of 1 centimeter radius and so on. And now we'll draw a smooth curve and this is the cam profile. So
Alright, so this blue line here is the cam profile connecting. Then we will just connect it with the return dwell. We will now have the cam profile.
in this way, we can draw the cam profile in case of the oscillating roller collar. Thank you very much for watching.
So you can see a pattern here. First, to draw the cam, we are first basing it on the behavior of the follower. So if the follower is reciprocating, if the follower is uh, oscillating, given the distance of the travel of the follower, so it all depends on the motion required for the follower. Then once we have drawn the references, you can now trace the cam profile, and as you can see, the cam profile has different kinds of shapes. Again, this is a hard one when drawing the cam profile for oscillating. So this is very challenging in comparison with reciprocating followers. Then I have one last video. So I have given you samples on how to draw the cam profile. For reciprocating followers, we have knife and we have roller follower. For the flat-faced follower, it's the same method with the knife type method. So it's just the same. Because the only different one is the roller because it has a prime circle. So only the roller follower has the prime circle. So I given you examples for inline reciprocating. For the last video, for the last lecture or example, we will now see how to draw an offset type of follower. First, we will see how the cam profile is drawn while it is inline. Then, we will see how it will be drawn if it is offset. So, for the offset, we will have a different approach.
In this video, we'll see how
To simplify the lecture, we will just use a constant velocity.
to
So, it's
draw
just a
cam profile in case of offset knife edge follower. So let us start with the problem statement over here. We have to draw a cam profile to operate the inline knife edge follower using following data. Outstroke with uniform velocity for 60 degree of cam rotation. There is no dwell period between outstroke and return stroke. Then return stroke with uniform velocity for next 60 degree of cam rotation. Lift or stroke of the follower is 40 mm. Base circle radius is 43 mm. And now if there is an offset which is provided on the right hand side of 12.5 mm, then how you will draw the cam profile. So this is the important part in this particular case. So there are two cases. First one is that we'll draw the inline knife edge follower, the cam profile in case of inline knife edge follower, and then for the offset follower. Now the data which is given over here is outstroke is 60 degree. There is no dwell between outstroke and return stroke. So return stroke is 60 degree. Outstroke dwell is 0. Then return dwell will be 360 minus summation of this particular. But this is of no use for us while drawing the displacement as well as for the cam profile. Lift or stroke of the follower is 40 mm or 4 centimeter. Minimum radius or base circle radius is 43 mm. And offset of 12.5 mm is provided on the right hand side. Now let us choose the scale for this. So on x-axis we are having 1 centimeter is equal to 10 degree of cam rotation. On y-axis we are having 1 centimeter is equal to 10 mm of lift or stroke of the follower. Now as the outstroke is given as 60 degree, 60 divided by the scale that we have chosen is 10. So 60 divided by 10, that is 6 centimeter. So we are going to draw outstroke with 6 centimeter on the.
So for this example, let's just go back with the given. So we have a knife edge follower type with the outstroke with uniform velocity. So just a simple diagonal on the cam displacement curve for 60 degrees. So there is no dwell. Then the turn stroke is also 60 degrees. Then the lift, which is the y-axis, is 40 mm. The base circle radius is 43 mm. So we can draw the base circle here. Then later we will have the offset at 12.5 mm. It will be shown on the right hand side. So RHS means right hand side. So by definition, when we say offset, it is that the center line of the follower is not coincide with the cam axis. So we will adjust 12.5 millimeters to the right later after the first example.
Lift or stroke of the follower is 40 mm or 4 centimeter. Minimum radius or base circle radius is 43 mm. And offset of 12.5 mm is provided on the right hand side. Now let us choose the scale for this. So on x-axis we are having 1 centimeter.
So this one is different because we usually use 1 centimeter is to 20 degrees. But since the outstroke is only 60 degrees, the scale is changed into 1 centimeter is to 10 degrees. So again, since scale is something we decide on as designers, it will depend on the situation.
centimeter is equal to 10 degree of cam rotation. On y-axis, we are having 1 centimeter is equal to 10 mm of lift or stroke of the follower. Now, as the outstroke is given as 60 degree, 60 divided by the scale that we have chosen is 10. So 60 divided by 10, that is 6 centimeter. So we are going to draw outstroke with 6 centimeter on the displacement diagram. Similarly, return stroke also of 60 divided by 10, that is 6 centimeter. And lift or height of the follower is 40 mm on y-axis. So 40 divided by scale is 10 mm. So 40 divided by 10, that is 4 centimeter on y-axis. Now let us start with our displacement diagram. So first we'll draw 6 centimeter length and immediately 6 centimeter length for the return stroke, and remaining is the return dwell, which is of no use. Then we'll divide this outstroke into 6 equal parts as shown over here, and return stroke also in the 6 equal part. The lift or height of the follower is 4 centimeter as shown in the diagram. So vertical height is of 4 centimeter. Now outstroke is taking place with the uniform velocity. So we have to draw this diagonal, and return stroke is also of the uniform velocity. So mark the various parts which we have made. So we have divided outstroke into 6 equal parts. Similarly, return stroke also into 6 equal parts. Now the vertical lines, they will intersect at A, B, C, D, E and F and so on. So vertical line from 1 will intersect this red line at A, 2 will intersect this particular uniform velocity curve at point B, 3 will be intersecting at point C and so on. So all these distances, that is 1A, 2B, 3C, 4D, 5E, 6F, 7G, 8H, 9I, 10J, 11K, all these particular distances, they are important for us from drawing the cam profile point of view. So let us start with our first part. That is the first case, that is the inline knife edge follower.
So to see the difference between the inline and the offset, first we will design on an inline type of follower.
So we'll draw the center line as indicated over here. Then the minimum radius of 43 mm or 4.3 centimeter. Now the outstroke is of 60 degree and it is converted into 6 part on the displacement diagram. So 60 divided by 6, so 10 degree. So we'll mark the 10 degree. We'll divide the outstroke of 60 degree into 6 parts, that is 10 degree each. Similarly, return stroke is also of 60 degree. So 60 divided by 6, that is 10 degree. So total is 120 degree, that is 12 equal parts we have to make. So as you can see, we have done the 12 equal parts of 10 degree each, 60 degree for outstroke and 60 degree for the return stroke. Now we have to transfer these distances 1A, 2B. So as you can see, this is 1A, this is 2B, 3C. You can see these red lines which are appearing over here. Measure this 4D, 5E, 6F, similarly 7G, 8H, 9I, 10J and 11K, and transfer these particular lines or distances. So 1A distance is transferred over here on the first line, as you can see. Similarly, 2B is transferred over here, 3C, 4D, 5E, 6F, then 6F, 7G, 8K, 8H, 9I, 10J and 11K. All these distances, they are transferred over here. And these are nothing but our A, B, C, D, E, F, G. And then we have to draw a smooth curve passing through this. So this is nothing but our cam profile in case of the inline knife edge follower. Now for the offset follower, we have to be very careful. First we'll draw the base circle of 43 mm or 4.3 centimeter. Offset follower.
Okay. So this is what it looks like for the inline type for this cam displacement curve. Now we will see how to draw the cam profile if the follower is offset. And for this one, for this example, is uh, when designing the cam profile for inline and offset, the cam displacement curve is the same. So meaning, this cam displacement curve that we have made earlier is the same cam displacement curve we will use regardless of if it is inline or offset.
We have to be very careful. First, we'll draw
So given here is that the center of the center line of the follower is offset 12.5 millimeters on the right hand side, meaning from the center of the base circle, we will find 12.5,
the
and
base
to make it an easier reference, we will make a small circle inside the base circle having the radius of 12.5.
circle of 43 mm or 4.3 centimeter. Then there is a offset of 12.5 centimeter which is provided on the right hand side. So draw a vertical
So this second line here, this vertical, this is the 12.5 offset from the center line, meaning the follower will start on this line instead of the usual on the middle one.
line, as you can see. Wherever it cuts the base
Okay? Then the intersection of the base circle and this offset line, we will connect a radius, and this radius will be our starting position.
circle, from that particular point, you have to join it with the center of this particular base circle. Construct a knife edge over here along with the guides. Now this is the knife edge with
Okay, so to better understand here, so this will start with the first one. So the knife edge follower with guides. So guides, this is the frame or the ground. So the knife edge follower is sliding. So this guides is the representation of frame or ground. Then this diagonal reference from which angles are to be marked. So the 60 degrees of the outstroke will be measured starting with this line. So in the past examples, we started with the outstroke in this y-axis. Then for this offset, we will start with the 60 degrees using this line. Then the turn stroke. Then base circle again is 43 mm. Then we will make a offset circle. So this offset circle will be crucial later. But for now, let's divide this base circle into parts for the outstroke and the return stroke.
guides, knife edge follower with the guides. Then this is the reference from which we have to mark the angles. Up till now, we are marking the angles from this particular vertical center line. This is the base circle radius of 43 mm or 4.3 centimeter, and this is the offset circle of 12.5 mm or 1.25 centimeter. Now we have to mark the angles from this. So first one is 60 degree divided by 6, that is 10 degrees. So we'll divide this 60 degree into 6 parts, that of 10 degree each. Similarly, return stroke also of 60 degree divided by 6, that is we'll divide this 60 degree into 6 equal part of 10 degree. So total will be 60 plus 60, that is 120, and 120 divided by 12, that is 10 degree. So we'll divide this into 12 parts of 10 degree each. So
So let's mark the 60 degrees of outstroke and 60 degrees of return stroke.
we'll divide this, as you can see, 60 first 60 degree for the outstroke and remaining.
Okay. With this example, we can already see that it is very different. It is very different with the other one, as this has its starting point at a different location.
For the return stroke. Now we'll mark this particular point. So 1, 2, 3, 4, 5, and 6. These first 6 parts are for outstroke and remaining 6 parts from 7 to 12.
Then, to transfer the distances we have made on the cam displacement curve, it is not as simple as what we did earlier. So what we did early on the other examples, from the divisions of these lines, we just extend it based on the measurement we have on the cam displacement curve. But here on the offset, we will make tangent lines. So to make tangent lines, these numbered points 1 to 12, we will connect it to the offset circle using a line that will tangent the offset circle. Then this tangent line is where we will add the measurements in the cam displacement curve. So again, this is not as for the transferring of the measurement from the cam displacement curve going to the cam profile, it is not as simple as what we did earlier. So earlier, we just put the distances on these division lines and trace it to have the cam profile. Here on the offset, what we will do is make tangent lines from the numbered points going to tangent the offset circle. Then this tangent line is where we will add the distances here from the cam displacement curve. So you will see here.
Therefore, the return stroke. Now mark these points on the base circle and remove these particular lines. And now the most important part, we have to draw the tangent to the offset circle from this point 1. So see the tangents that we are drawing. So we have to mark the tangent from the respective point 1, 2, 3, 4, 5. So we have to draw the tangent from these points to the circle, that is this particular offset circle.
So this is what I mean when we have to draw tangent lines. So we have made tangent lines from the numbered points going to the offset circle. So this tangent line here where we will add the distances measured from the cam displacement curve.
Like this. And then we have to transfer the distances, that is 1a distance we have to transfer over here, then 2b distance, then 3c, 4d, 5e, 6f, 7g, 8h, 9i, 10j and 11k. All these distances now we have transferred over here. So measure this distance 1a, transfer it over here, correct, like that. Then 2b distance, that also we have transferred. And now draw a smooth curve passing through the points a, b, c, d, e, f, g up to k. And this is the cam profile in case of the offset knife edge follower. So in this way we can draw the cam profile in case of the offset follower. Thank you very much for watching.
So that's the different methods or approaches in designing the cam profile. Again, these videos and the presentation I made for the discussion of cam is already uploaded in our Google Classroom, because on design plate number 3, we will be drawing a cam profile for a roller follower with offset um, installation. So that's it for today. Thank you for attending the class. Do you have any question for the step-by-step procedure of how to draw the cam? Do you have any question regarding our schedule that I have presented earlier? Masakit na ako dun. Okay, so if there was no more questions, let's see each other again on Saturday. Thank you for attending the class.